students. Title of today's lecture is Secondary Ion Mass Spectroscopy. So you can see from its name itself that there is word ion here. It means this technique is ion beam based technique. So what happens in a ion beam based technique? You can see from here. So when an incoming ion beam, so this is a incoming ion beam, when it interacts with the sample which we want to characterize, so many possibilities occurs. So if this incoming ion beam reflect from the sample, so it can cause sputtering. It can create or it can give rise to one characterization technique which is SIMS. In today's lecture, we are going to discuss about this particular technique. There is another possibility which is RBS. So that is also a material characterization technique. If this incoming ion beam get absorbed into the material, then we say that ion implantation has occurred. And if this interacting ion beam give rise to or to emission of certain photons, then it is photon spectroscopy. If particles are emitted, then it is if X-rays are emitted, then it is called particle induced X-ray emission. And there is possibility of electron emission also. So all these phenomena give rise to certain techniques. Some are characterization technique and some are processing technique. But in today's lecture, our focus is on the discussion of SIMS. SIMS, the full form is secondary ion mass spectroscopy. What it is? If we talk about the working principle of this technique, the basis of this technique is actually a destructive removal of material, right? It's a destructive removal of material from the sample by sputtering and analysis of ejected material by mass analyzer. So actually what happens in this technique? So suppose this is the sample which we want to characterize and there is a incoming ion beam. So this ion beam is known as primary ion beam. So you can look at the sample, two kind of circles are there. So open circles and filled circles. So open circles can be assumed as the host atoms and these filled circles can be assumed as some impurities embedded into this material. So when this primary ion beam strikes this sample surface, it causes sputtering here. So the atoms of the host material, they are ejected out. So the impurity atoms which were present in this portion, they are also going out of the material. You can see here open circles as well as filled circles are present here. So all the ejected material atoms, they have to be analyzed by a mass analyzer. It means we can identify the mass number of all these species. That way we can identify the element which is there in the ejected material. And so it's possible to identify the impurities which are present here in the material. So that kind of benefit we can get in this SIMS. If we talk about the block diagram of this instrument, so the basic block diagram look like this. So incoming ion beam is there. So first we have to select a certain kind of ions to act as a primary ion, because the selection is very important so that we can get highest possible yield when the sputtering takes place at the sample surface. So the ions and the atoms which are ejected out of the sample material, they are called secondary ions, and these secondary ions have to be analyzed with the help of this mass spectrometer. So through this mass spectrometer, when these ions passes, we can identify their mass number and then we can plot this information maybe like this. So if you plot it like this, here on the x-axis we have mass number and on the y-axis we have intensity for that particular mass number, right? So mass number peak we will get if there are sufficient or there are large number of elements of that particular mass present into the sample material. So we can connect it to the ion counter. We can count the number of ions of a particular mass. We can put this information on the CRT screen also, and it's also possible to get depth profile like this. So here what happens, on the x-axis we have depth and on the y-axis we have intensity. So it's possible that we keep on striking this ion beam here, and whatever ejected elements are there, we can see their concentration variation as a function of depth. All this kind of information is possible using this technique. So you can say that this seems is actually a surface analysis technique. So we are ejecting atoms from the surface of the sample, and we are analyzing them, and we are identifying what particular element or what particular atom is present here by finding out its mass. So it's a surface analysis technique which is used to characterize the surface and subsurface region, right? So not just surface, but even the subsurface. We can go below the surface also, and based on mass to charge ratio. So actually, when we talk about this mass spectrometer, it is not identifying only mass. It is actually identifying mass to charge ratio. But the mass to charge ratio is also different for different elements because electronic mass is same. So this mass to charge ratio differ because they have different mass number, right? Now, if we talk about the instrumentation used into the SIMS, so the instrumentation look like this. So the major components of this instrument, they are indicated here. So first thing is a primary ion source. This primary ion source you can see here. This is primary ion source. So this generate a ion beam. So this ion beam is focused and allowed to fall on the sample surface. This is sample here, and in response to this incoming ion, what happens? Secondary ions will go out of the material. So actually sputtering is taking place here. So the secondary sorry, ions which are ejected out of sample, they are extracted through this extraction electrode, and then after this ion extraction, we perform this mass analysis. All this part you can see here, this mass analyzer, right? All this part, this is mass analyzer. So the job of this mass analyzer is to separate out atoms or species of a particular mass to charge ratio, and then it is allowed to fall on the ion detector, right? So when it reaches to the ion detector, then it is confirmed that the atoms of this particular mass to charge ratio are present into this beam, right? And if we talk about the mass analysis part, so there are three different techniques. So quadrupole, a magnetic sector, and time of flight. So all of these three techniques have their advantages and disadvantages, but any one out of these three techniques is used for the mass analysis purpose. Now another important component in a SIMS is vacuum. So the vacuum is very important. So all these functions take part into ultra high vacuum. It's very necessary because if vacuum is not there, it becomes impossible to form a ion beam and to focus it on the sample surface. Because if the gaseous species or atmospheric gases are present here, these ions will not be able to reach to the sample. Not only the primary ion source, even the secondary ions which are coming out of the sample, their energy is not that much high. So if there are other gases or atmospheric gases are present in the surrounding, so these ions will not be able to come out, and that way they cannot be identified by the mass analyzer, and they cannot be detected by the detector. Another important reason for using ultra high vacuum is that all these have to be in a contamination free environment. If contaminations are present, they will also get detected and they will act as a impurity into the system. They will affect all our measurement. So we have to make it contamination free, and we have to allow all ions to move freely to its designated place, and that's why all these functions are performed, all these components are enclosed in a ultra high vacuum chamber. Now we will discuss some of these components in more detail. So first we will talk about the primary ion source, what kind of ions can be used as a primary ion source, and we will also discuss about this mass analysis technique. So if we talk about the primary ion source, so what kind of ion we have to use as a primary ion, that depends how much beam current we want and what kind of species we want to detect into the sample. So if we know these things, then we can decide what kind of ion is suitable to perform that particular task. So we have uh, if we talk about the primary ion source, you can see. So the two choices are there. We can use oxygen ions or we can use cesium ions. These are the most popular primary ion sources in case of SIMS. Now you can see here uh, the periodic table is given here. This periodic table shows the all the elements and how much is yield, or you can say what kind of primary source is suitable for this. So if you talk about these ions, or sorry, these elements which are indicated here in the green part. So if we have to detect these particular kind of a species into the sample, then the suitable primary ion beam is cesium based. So you can see here, if we use cesium primary, then all the elements which are indicated in the green color, they can be sputtered from the sample very easily. And these elements which are shown in the green color, they are actually negative secondary ion, right? And if our purpose is to detect the elements which are indicated here in this yellow color, then we have to use oxygen as a primary ion beam, right? For example, you can see here, if we are using oxygen ion beam as a primary source, then it becomes very easy to detect boron and aluminum in silicon, right? They form actually a positive secondary ion. So you can see here boron and aluminum. Boron is here, this boron and aluminum. They are indicated here in yellow color, and yellow color means we can use oxygen as a primary ion. And if we have to detect phosphorus and arsenic in silicon, so phosphorus and arsenic, they are as an impurity into the silicon, and if we have to characterize that kind of sample, we have to find out the first we have to identify whether phosphorus and arsenic are present there, and then we have to also estimate how much is their concentration into the silicon. So if we want to perform that kind of task, then we have to choose cesium ion as a primary ion beam. You can see here phosphorus and arsenic, so they are here, right? So and they are in the green color. It means we can use cesium primary ion source for this purpose, right? And the phosphorus and arsenic, they are actually negative secondary ion in silicon. So that way you can see that what kind of primary ion source we have to use, that depends what kind of species or what kind of atoms we have to detect from the sample surface. Now having some idea about the type of primary ion source, now let's move to another important sector in case of SIMS, and that is mass analyzer. So you know that there are three different kind of mass analyzers possible. So first we will talk about this magnetic sector analyzer. Sorry. So you can see here in this slide, so the sample is somewhere here, right? So when the primary ion beam is striking here the sample, so the secondary ions will be emitted, ejected out from the sample, and these secondary ions, they are focused in the form of a beam, and they coming out of the source exit, right? So these are secondary ion which are going like this. So first they enter into a electrostatic sector. So what happens here in this electrostatic sector? You can see there are two parallel plates, and these plates are bended like this, right? And there is an electric field here. So this plate is positively charged and this inner plate or is negatively charged. So there is an electric field, and the direction of electric field is something like this, right? Now because of this electric field, these incoming ions, they get a force towards this and they will bend like this. they will try to follow the path shown by this electrostatic sector. Now, how much bending is there, that depends on the this electric field, and it also depends on the initial kinetic energy of the ions, right? Now, only those ions will be able to cross this electrostatic sector which have a suitable initial energy, right? So all the ions which don't have that suitable energy, they will either touch this plate or this plate before exiting, right? So a particular energy of secondary ions is thus selected in this electrostatic sector. You can see that only those ions who have this particular energy, they will be able to come out of this sector, right? So the electrostatic sector decides the energy of the secondary ions. And now once you have set the energy of the secondary ions, you can calculate their velocity also. Because this velocity will be calculated using this formula. The E is the energy, and this energy is equal to the kinetic energy, half mv square. M is the mass of these ions, right? So now you know how much is their energy, or you can say how much is their velocity. So once these secondary ions comes out of this electrostatic sector, they enter into the magnetic sector. This part is magnetic sector. All this part is magnetic sector. So once they enter into this magnetic sector, you know that a moving charge in a magnetic field experiences a force, and because of that force, it starts bending. So the bending is like this. So this bending is like this, and how much is the radius of curvature of this bending? That depends, of course, on the velocity of the incoming ions, and it also depends on the strength of magnetic field. And that bending depends on the mass of the, or you can say the bending depends on the mass to charge ratio also. So you can see here in this figure. So how much is centripetal force if this charged particle moves like this, and there is a perpendicular magnetic field here. So the centrifugal force is balanced by this magnetic force, and you can see that this R depends on many factors. This R depends on mass, it R depends on magnetic field, and R depends on the velocity of the uh, charge species also. So the velocity is decided by the energy of with which the carriers, or with which the ions are coming out of this electrostatic sector. This bending now is decided by the magnetic field and also by the mass of the ion. Now when they come out here, so you can see the ion detector or a ion collector is placed here. So ions of a particular mass only will be able to reach to this ion collector. So the ions of different mass other than a particular mass, they will hit this part either here or here, and that way they will not reach to the collector, and we will not be able to detect them. So that way you can see that this combination of this electrostatic sector and this magnetic sector help us to select the mass to charge ratio, right? Now suppose we want to detect a ion of a different mass, or you can say that if we want uh, a ion of a different mass to reach to this collector, then what we have to do, we have to change this magnetic field here or electric field here, so that we can change either their V, or we change either their B, so that we get a suitable value of radius of curvature in order to allow those particular ions to reach to this ion collector, right? So if we have to detect different masses or different mass to charge ratio, then continuously we have to keep on scanning the electric field and magnetic field. So for a suitable combination of these parameters, we will be able to allow the ions of a particular mass to reach to the collector, right? Now this is one particular technique for detection of mass to charge ratio of the secondary ions. Now let's talk about the second technique. This is quadrupole. So in this technique, what happens? We have parallel rods with an oscillating electric field. So you can see here there is this A, suppose this rod, and opposite to this rod there is another rod A dash. I am naming it. So there is a oscillating sorry, electric field applied between A and A dash. In the same way, there is B rod. This is B rod suppose, and this is your B dash. So they are also opposite to each other, and there is oscillating field applied between this B and B dash. Now the ion beams, secondary ions, which are passing through this short slit, they enters into this assembly, and you can see here the ions with a stable trajectory only will be able to cross this assembly, right? So this red line you can see. So these are the ions, and their trajectory is stable, and only they are able to go out of all this arrangement and also through this exit slit, and then they will be able to detect it. All other ions which have a different mass or mass to charge ratio, they will have this kind of unstable trajectory. You can see this blue line, and they will hit these rods before exiting uh, this this assembly, right? So you can see this blue line, this have reached only up to this particular point, and that way it will not be able to exit this assembly, right? So that way you can see that for a given magnitude of oscillating electric field, only a specific type of ion will be, a specific type of ion means the ion which have a particular mass to charge ratio, right? A fixed mass to charge ratio ion will be able to exit through this assembly, and all other ions will be trapped within this assembly itself. So that way, by choosing the suitable value of oscillating electric field, we can select one particular mass to charge ratio, and only that particular ion will be detected at the detector. So if we have to identify elements, because in the beginning we don't know what kind of elements are present into the sample, what kind of species, or you can say what kind of mass number is there in the sample. So we have to do the scanning of electric field, oscillating electric field here, and for each and every oscillating electric field we will keep on detecting, or we can keep on recording the reading on the detector. For some values of oscillating electric field only, we will get some reading at the detector, and then we will identify that what is the value of mass to charge ratio of the species which are reaching to the detector, and that way it is possible to identify the species which are present into the sample. So the advantage of this quadrupole arrangement is that it is less expensive as compared to that magnetic sector analyzer. But the problem is the resolution is not that much good. The resolution is low, and it cannot distinguish between ions with close mass to charge ratio. So if you see the table, you will be surprised to see that most of the many ions or many atoms, if you see their mass to charge ratio, the difference is very small, and that difference is you can see of the you can say second decimal place. So because of that small difference between mass to charge ratio of many species, it becomes very difficult to distinguish them using this particular technique. But the advantage is that it is less expensive. Now, the third technique for mass analysis is time of flight. So the advantage here is that you need not to go for scanning of electric field and magnetic field. You have seen in earlier two techniques, the scanning of electric field and magnetic field is necessary in order to identify the elements present into the sample. But here in this technique, that kind of scanning is not required. So what happens in this technique? So ions sputtered in short burst. So short burst means for small duration, you can see here, if this is a time pulse, only for the small duration, that duration may be 1 second or less than 1 second, Only for the small duration, this primary ion beam is supplying the ions. And since the primary ion beam is active only for small duration, so we will get secondary ion beam also for that particular duration only. Now, time of secondary ions to travel to the detector, that time we have to measure. So this is the portion where the secondary ions will be generated. So these will travel like this and they will reach to the detector. So how much is the time taken in order to reach to the detector after being ejected from the sample surface? That time will decide how much is their mass to charge ratio. So the relationship is given here. So mass to charge ratio you see here, it depends. This is the accelerating voltage, this is time of flight, and L is the distance between the sample and the detector. So what we have to do here, we just have to record how much is time. So we know that sorry, at one particular moment a pulse of primary ions is generated. That pulse will generate secondary ions. So that pulse, how much time takes to reach to the detector. So the time difference between the pulse which is ejected from the sample and the pulse when it is detected at the detector, that time difference we have to note down, and that will give us information about the mass to charge ratio. And that way, from this mass to charge ratio, we can identify what kind of element or which element is present into the secondary ion field. Now, the advantage here is that both very large and small ions can be detected using this technique. So there is no any issue in that. Unlimited mass range. So it's obvious in the earlier point also we have indicated that whatever is the size of the ions and whatever is the mass of the ions, we can detect it irrespective of all these things. And another important point is in this kind of arrangement, the primary ion current that need not to be very high. So we can work with low primary ion current also, and if we can work with low primary ion current, that is advantageous also, because in the next slide you will see the static seams that is possible if we are working with low primary ion current, right? Depth profiling can also be done, and that uh, is possible only like for a short range, maybe about 10 nanometer range, not more than this, because the primary current is very less here. For depth profiling, we need large current, but the low current is advantageous as far as static SIMS is concerned. So now we understand the basic components which are part of the SIMS instrument. Now we go to the other points. Now, for example, let's talk about the analysis mode. Now, three kind of analysis modes are possible in case of SIMS. One is static SIMS. Just in the earlier slide, we were talking about it. Sorry, what happens in static SIMS for low incident ion beam current? You can see here, or you can say for low sputtering rate. If the ion beam current is low, sputtering rate will also be low, and that is about 0.1 nanometer per hour. So for 1 hour, we keep on doing this all this analysis, and we are removing only zero point 0.1 nanometer uh, layer from the top surface. So you can say that the static SIMS is true surface analysis technique. So a complete mass spectrum can be recorded for surface analysis of the outer zero point 0.5 nanometer or so, right? So the spectrum is like this. Slowly, we are sputtering the top surface. So on the x-axis, if we see spectrum, that is mass number, and on the y-axis we have intensity, or you can say the count, and the peak amplitude that indicates the relative concentration of that particular mass number into the sample, right? So for example, if you talk about this and if you talk about this, so this blue line indicates that this particular mass number element is present into the sample in large amount as compared to the other one, right? So that way, static SIMS, you can say it's true surface sensitive technique, and the low ion beam current is used here, and the sputtering rate is also very small. And if we talk about second mode, that is dynamic SIMS. So in dynamic SIMS, what we have high sputter rate, and of course beam current also have to be high if we want to go for high sputter rate. So what we do here, so intensity of one peak, or you can say for one particular mass is recorded. So in static sims, we are recording information about different mass numbers by changing. If you talk about mass, the magnetic sector analysis, we keep on scanning the magnetic field and electric field in order to get information of all possible mass numbers which are present in the sample. But in case of dynamic sims, we fix the magnetic field intensity and electrostatic field intensity in such a way that our focus is only on one particular mass number, or you can say the focus is only to detect the concentration of one particular species. So we tune our system for one particular species by fixing magnetic field and electrostatic field. Now we keep on sputtering the sample surface slowly with time, and that way we keep on recording the variation of concentration of that particular species as a function of depth. So the information is plotted like this. So x-axis there is sputtering depth, and this red line is one particular mass number, and this blue is different, and this green is different. So at a time normally we focus on one particular species, but that kind of measurement can be repeated to get information about the multiple species also, right? So sputter rate is high, you can see about 10 micrometer per hour, right? And in static sim you can see in 1 hour we were removing only 0.1 nanometer. So static sims means purely surface measurement, dynamic sims means depth profiling. Third kind of analysis is also possible, that is imaging sims. So that is almost similar to the static mode, right? The only thing is that only difference is that here the information is not plotted like this kind of spectrum. So information is in the form of a 2D image, or you can say map of samples based on the concentration of ions. So if the information is plotted something like this, right? Now let's talk about the advantages of sims. Sims, we can detect a number of elements, or you can say the almost all elements in the periodic table. They can be detected if they are present into the sample. And not only the elements, their isotopes can also be distinguished, because here our focus is not on a particular atomic number. The focus is on the atomic mass, right? So even element having different atomic mass means isotope, they can also be distinguished very easily. Now detection limit is very high. Parts per million is possible for most of the elements, and even parts per billion, that is also possible for some favorable elements. Now depth resolution is 2 to 5 nanometer depth, that much we can go very easily. And the lateral resolution, of course lateral resolution depends on the beam diameter also, but it's possible to get this lateral resolution 20 nanometer to 1 micrometer. I Interesting thing or very good thing is that even the insulators can be analyzed. It's not like that in case of scanning electron microscope. So if there are insulating materials, then there are problems because the surface gets charged because of the electron beam. But here in this technique, that issue is not there because the material is being sputtered, right? So the insulators can also be analyzed, and the chemical information obtained from relative molecular ion abundance. So we can get chemical information about many kind of. If we talk about the disadvantages of this, so the mass interference, so that is possible. So we are detecting here masses of the species which are present in the sample. So the mass interference because of some other uh, uh, elements having like similar kind of mass, so that kind of problem can occur. Now secondary ion yield vary by more than 6 order of magnitudes over the periodic table. So if you look at the periodic table, you will see that there are large number of elements, and theoretically it is possible to detect all the presence of all those elements using sims. And not only their presence, we can have some estimate about their concentration also. But the issue is that sorry, Yield of secondary ions that varies if we move in the periodic table from one element to other element, and that variation is of the order of 6 order of, right. So some elements, if we see their yield is very small, so for the same beam current, they will be sputtered like in less quantity and less number, and some elements they get sputtered easily for the same beam current, and we get higher yield. So those kind of issues are there, and because of that, sometimes it becomes difficult to get the exact estimate of the concentration of the impurities or species present into the sample. Now, secondary ion yield are often matrix dependent. What it means? For example, if we talk about silicon, so we want to detect how much silicon is there, right, or whether silicon is present or not there. So it all depends on the yield of silicon. So for the same beam current, you will see if we do the if we analyze the secondary ions ion beam, I mean, if we analyze like yield of, if we see the yield of silicon in SiO2, suppose we have a SiO2 sample, right? And in SiO2, yield of silicon is very large. But if we talk about the yield is very large. But if we talk about the silicon wafer, where silicon is present in very pure form, there is no bonding with any other species. So in that case, if we talk about the yield of silicon, that yield of silicon is comparatively low. So that kind of effect is known as the matrix dependent effect. So we cannot say that the yield of this particular species is this much. So the yield of the same element keep on changing depending on its background, in what kind of sample it is coming from. So if silicon is coming from pure silicon, its yield is yes. If silicon is coming out from a silicon dioxide sample, then its yield will be more. So sometimes it becomes difficult to handle these kind of situation where the secondary ion yield is matrix dependent. Now another issue here is that the flat surface is required for best depth resolution, right? And if already it is a flat surface, then it is good thing, otherwise it can give you some error. Now it is a destructive analysis, that is also important thing. So you have seen from the first slide itself that there is removal of material from the sample surface. So the sample which you are characterizing using SIMS, that cannot be used for any other kind of analysis or for any kind of purpose later on, because the sample is finished, right? So these are the disadvantages of SIMS. So I hope that that now you understand the working principle of SIMS, what kind of information we can get from SIMS. You know the instrumentation of SIMS, what are the various important components which are part of SIMS instrument. You know various mass analyzer techniques. You understand various modes of operation of SIMS, and you also understand the advantages and disadvantages of SIMS. So still, if you have any question or any doubt, you can discuss with me in the interaction. So thank you very much. Thank you.